Thanks, Christina, for the very nice introduction. It's a pleasure to be here. Actually, it is kind of forced me to think when it was the last time I gave a talk in Taiwan, and I found out that this was in 2010, and I was still a PhD student back then, and it was in this very same room. So it's nice to be back 15 years later. So as Christina mentioned, my talk is going to be focused on accreting supermassive black holes, and in particular I'm going to be talking about the millimeter continuum. But let's say I use this as a catch in a way. I'm going to talk a lot about the millimeter continuum, but I'm going to start talking about X-ray radiation, just because the work we have been doing with my group over the past few years has been focused on the relation between the emission produced in the millimeter and the emission produced in the X-rays in these accreting supermassive black holes. So I will start giving a little bit of a framework on why we study AGN in the X-rays, and then from there I will discuss the problems that are caused by obscuration in these accreting objects, and from that I will move on discussing the millimeter and show you some more recent development that has been achieved by our group thanks to ALMA observations. So in other words, I will tell you how an X-ray astronomer happens to be in Chile and learns how to do high energy astrophysics with ALMA, because you know it's available there and it's just amazing. So starting with X-ray emission in AGN. So X-ray are a very useful trace of accretion. Actually, they are an ubiquitous signature of this process, and this extends over a very large range of masses, going from the protoplanetary systems in which X-rays are produced by shocks and this sort of processes, up to higher masses. So for example, X-ray black hole binaries, where most of the X-ray emission is actually produced by the accretion disk or by some plasma located very close to the supermassive black hole, and up to the highest masses, and those are the intermediate and the supermassive black holes. And here we are talking about masses that can go up to 10 to the 10 solar masses. X-ray emission is actually a very good trace of accretion onto supermassive black holes. Here I'm showing you some old image from the Hubble Deep Field North. This is a HST image. You can see here a lot of beautiful galaxies. When you look at the same field with Chandra, you see only a few sources, and that is because galaxies don't emit very strongly in the X-rays, so one is picking up mostly the accreting supermassive black holes. In these accreting supermassive black holes, the emission in the X-rays produced by a plasma that is very close to the black hole. So here I'm showing you a figure from a recent review that we published a few years ago with Cristina Ramos Almeida of the structure of active galactic nuclei or accreting supermassive black holes. You have the scale here. This is the logarithm of parsec. The black hole is here at the center. Then you have the accretion disk, that is what is powering most of the optical UV emission, and that's what's basically fueling the black hole and allowing it to reach the masses of 10 to the 9 or 10 to the 10 solar masses. Larger scales, you have some photoionized gas. It's this BLR broadline region, and this is basically gas that is moving very rapidly around the supermassive black hole and is emitting broad lines in the optical UV. And the larger scales, you have gas and dust that is typically distributed in some sort of anisotropic way, and we usually call it the torus. And this dust is also observed in the polar regions here, and this is possibly associated to outflows, which one can see on larger scales, and then on very large scales, so hundreds to thousands of parsec, there is the narrow line region. This is again photoionized gas, but the lines here are produced by gas that is not moving very rapidly, so they're very narrow. And here is the source of most of the X-ray radiation. This is something I would like to focus on because we're going to discuss a lot about this X-ray corona also from the millimeter perspective. So those are electrons that are moving very close to the supermassive black hole and have very high temperature. These electrons, again here we have the schematic structure with the black hole and the corona. These electrons are basically upscattering the optical UV photons that are produced in the accretion disk into the X-ray regime, just giving energy. And this X-ray emission can extend up to a few hundred keV, as you can see here, and it takes a shape of a power law continuum with high energy cutoff. And the high energy cutoff is basically telling you something about the temperature of these electrons, because obviously the electrons cannot upscatter the radiation to energies much higher than their temperature. They typically have a thermal distribution, but we think that there is also a non-negligible non-thermal component that can go up probably to a few percent. And I'm going to get back to that later. So the X-rays are produced very close. So here the scale is probably a few gravitational radii, half a light hour, 1 light hour, depending obviously on the mass. But since they are produced so close to the system, they can actually illuminate it and give us some understanding of the circumnuclear properties. One thing I wanted to mention, while X-rays are actually very useful, they are typically energetically not very strong. So you have less than 5 to 10% of the total AGN emission that is produced in this corona. As for what produces these thermal electrons, there are several theories. Since this is a structure that is very close to the black hole, we have only indirect measurements, but there is a number of theories that predict that this might be associated to magnetic reconnection, and this is why the name is originally the name of corona was given to this structure in analogy with the solar corona. Or it's possible that this is just an aborted jet, accreting supermassive black holes that can develop very strong jets that are particularly visible in the radio. But in some cases it's possible that this jet fails to develop, so the hot electrons stay there, and this might give rise to this comptonizing plasma.
Optical depth.
Sorry?
What's the optical depth?
Typically it's like between 1 and 2.
1 and 2.
Yeah, it can be a bit higher. I mean, depends. Again, we don't really have a direct constraint. We mostly measure optical depth and temperature with comptonizing model just spectroscopically.
How do you discriminate jet and corona emissions?
Well, the jet is not expected to produce a lot of X-ray radiation, particularly in sources that are so-called radio quiet, in which you don't have very strong jet emission across the electromagnetic spectrum.
So you consider a relatively large accretion rate?
So those are, yeah, mostly like we are focusing on the bulk of the AGN population that is observable in the X-rays, and those objects, they have...
That's why you assume corona in that position. Okay.
Yeah. And we know that this region is compact also because it's very variable. So this is an X-ray light curve of a relatively low mass AGN, and you can see that there is a lot of variability, a factor of 2, just within hours. So as I was mentioning, we actually have constraints on this X-ray emitting plasma, mostly from spectroscopy, and fitting comptonization models, we can infer things such as the temperature and the optical depth. We know that this temperature is typically a few hundred keV, so the temperature of the plasma is somewhere around 10 to the 9 Kelvin. And this is a recent work in which basically we collected all available broadband X-ray spectra, and we were able to infer this cutoff energy. The problem is that it's very hard to get good constraints on this quantity, so the amount of lower limits is very large, and this is highlighted here by the red dashed line. You can see that actually we have way fewer measurements than lower limits. Okay, so I'm not going to dwell too much on this. If you're interested, I'm finalizing a large review on the topic for reviews of modern physics, which I hope will be available soon, maybe somewhere around the end of this year. But X-rays are a great probe of AGN emission, but they are also extremely useful as a probe of the circumnuclear environment, because as I was mentioning earlier, they are produced very close to the accreting system. So again, here we have the cartoon, the black hole at the center, the accretion disk, and all the other circumnuclear components. And while we detect this primary power law continuum that comes directly from the corona, this corona is also illuminating the surrounding material, and in doing so is producing some very well distinguished features, such as the iron K alpha and Compton hump at 30 keV, that are basically tracing this gas and dust that surrounds the black hole. So in principle, we can study some of the characteristic and physical properties of this obscuring material, which is very hard to resolve observationally, just by looking at X-ray spectroscopy. The other thing that we can do is to use obscuration, because obscuration can leave a very strong imprint into the X-ray spectrum of AGN. So I'm going to show you here just a video of an accreting system. So you have the black hole here at the center. Those are clouds from the torus or the BLR. And here you have the spectrum, the same spectrum that you saw earlier in the other cartoon. This is the K alpha line. Here you have the Compton hump. So I'm going to show you how actually obscuration affects the X-ray emission of AGN. So the video is showing here. So what is changing now is the line of sight towards the center, and you can see that as more gas and dust crosses our path and the source is obscured, you start seeing some photoelectric absorption. When the obscuration becomes very strong, then you have a very strong impact of Compton scattering, and at that point a lot of the flux is depleted and you're actually only able to see the reprocessed X-ray radiation. So as the obscuration increases, we see less and less of the intrinsic X-ray emission, but we can use the very clear imprint that obscuration leaves on the X-ray spectrum to measure how much gas and dust there is in the line of sight towards the AGN. And so this, in principle, it's both a curse and a blessing, because obviously it complicates our life when we look for AGN, but it can allow us to say something about the general properties of the circumnuclear material. In particular, if we are looking at surveys, so large number of accreting supermassive black holes, and we have a good completeness, we can use the line of sight column density for hundreds or thousands of sources as a tracer of how much material there is around the supermassive black hole. So say that you have a survey with high completeness, 50% of the sources are obscured, and you are sure that you're recovering all sources. You can say that in average, half of the sky of the accreting supermassive black hole is covered by gas and dust. So over the past few years, we have been using hard X-ray surveys to understand more about the circumnuclear environment of these accreting supermassive black holes. And one thing we have been doing is to look at objects that were identified by the SWIFT-BAT survey. SWIFT-BAT is a hard X-ray instrument that is observing the whole sky between 14 and 200 keV, and that has detected about 1000 AGN. SWIFT-BAT was originally conceived to actually detect gamma ray burst, and in doing so, it's been scanning the sky looking for this gamma ray burst, and has been detecting quite a lot of AGN. Those are very bright AGN in the local universe. So here I'm showing you the luminosity versus redshift for the SWIFT-BAT AGN, which are these objects here. So these are mostly the radio quiet, rapidly accreting AGN, and those are the blazars here as triangles. And here you have surveys that have been carried out by other X-ray instruments at much higher redshifts. And you can see here that while SWIFT-BAT doesn't get to high redshift, is probing a population that is actually quite similar to the population of AGN that is detected by these surveys. So by studying this nearby AGN in the hard X-ray band, we discovered that actually most AGN in the local universe are obscured. So here I'm showing you the fraction of sources versus column density, and this column density again tells you how much gas and dust you have in the line of sight. And you can see two lines here. In red you have the observed distribution, and in black the intrinsic. So we can concentrate on the intrinsic, which is basically the histogram once it's corrected for the selection function of the survey. Because even in the hard X-rays, when one is able to detect actually more flux from the AGN for a high obscuration, there is still a lot of objects that are lost. And from this you can see that there is a very large number of obscured objects, and here the threshold we typically use is about 10 to the 22. So about 70% of the AGN in the local universe are obscured.
But look, NH is from the spectrum cutoff. You infer from the low energy X-ray.
Yes, well, from the broadband fitting really, but in principle, yeah, this comes from both the photoelectric cutoff that you saw earlier, but also from Compton scattering.
But does it distinguish between dust and gas?
No, you cannot really distinguish. There are ways to do it with very high resolution, because there are some features in dust, like the XAFs, some edges that are actually larger when you have dust, but it's very hard, almost nearly impossible. It's been done maybe for a very few bright sources. There have been a few claims with Chandra, but in general it's very complicated. So you cannot distinguish. And in the X-rays you are affected both by gas and dust.
How do you know that this converges if you go to higher?
How do you know what?
How do you know that this doesn't keep going up as you go to higher?
We don't know. And I'll get there later, because actually we are a bit hopeless in the X-ray to go above this threshold. Because here, particularly if your covering factor, so the fraction of the sky that is covered by absorbing material is very high, there is very little flux, because we are mostly observing reprocessed X-ray radiation. But from this, we can basically build a very schematic cartoon of the circumnuclear environment of AGN, because this is telling us that about 70% of the sky is covered by this obscuring material, and about 1/3 of it by Compton thick material, which is the material with column densities above 10 to the 24. So this is just to say, as a key message to take away, that most AGN in the universe, even in the local universe, are heavily obscured. So we're talking about 70%. So obscuration is something very important. And as I was telling you, in the X-rays, we are kind of like cursed with this obscuration, because particularly in the soft X-ray regime, shown here by the red curve, we are missing out a lot of flux. So this plot is showing you the fraction of flux that is escaping the system as a function of column density. And you can see that already a few times 10 to the 22 or 10 to the 23, you are losing 50% of the flux. And this is where most X-ray satellites are actually observing. In the hard X-ray band, which is covered by instruments such as WIF-BAT, you are actually able to recover much more. But to go back to your question, if you look here, like above 10 to the 25, we are recovering only less than 25%, 20% of the flux. And this is the case in which you have enough of the sky that is open so that some scatter light can go out. But again, if you have 10 to the 25, as I will show later, and all your sky is covered, then there is no way to see these objects, even in the hard X-ray band, which is right now the best way actually to detect obscured AGN. And we are doing this mostly with two facilities, as WIF-BAT, which I mentioned earlier, and NuSTAR, which is the first focusing hard X-ray telescope, and which is covering a similar range as WIF-BAT, but only up to 80 kV. So here I'm showing you just an example of a situation in which actually without hard X-rays we would not be able to detect the presence of a heavily obscured AGN. So this is a merging galaxy. It's a pair of galaxies that you can see here. Those are selected from some infrared survey of mergers. This is actually a paper that we did with Christina a while back. It's a very nearby object. And you can see here the two objects are relatively close. And when you look at this NGC 6286, this object in a merger, just with the soft X-ray telescope, so Chandra and XMM Newton, you're able to reproduce all the emission just with a starburst model. But then when you plug in the hard X-ray data, one can see a very strong excess. So this is new star shown here in blue above 10 keV, and this comes from a low luminosity heavily obscured AGN that we are seeing just because this object is at 80 megaparsec, so it's close enough for us to do this. But put this same object at 200, 500 megaparsec, there would be no way to actually detect it. And indeed, we are really blind to this heavy obscuration, even with hard X-ray surveys. So here I'm showing you the fraction of sources that are heavily obscured, so Compton thick, as a function of the distance. So distance, I mean, we are really talking about the very local universe, up to 100 megaparsec. So here in red, you have the intrinsic Compton thick fraction, which means, going back to this plot I showed you earlier, once you correct your distribution for the selection effect, this is the number, the fraction of objects that you expect to be heavily obscured. We can just concentrate on the black points. In black, you have the observed fraction. Okay, so basically, like the fraction of objects that you see with the BAT survey, so the hard X-rays. You can see that within 20 megaparsec we are good. We recover all of them, so consistent with the intrinsic fraction. And already at 60 megaparsec, actually we are losing a lot. So we are blind to all this Compton thick AGN already at tens of megaparsec. And the problem is that when we look at surveys at higher redshift, we find that actually the number of obscured objects increases with redshift. So here you have redshift versus obscure fraction, again defined as the fraction of objects that have high column density.
In your last plot, the first bin which you use as your as kind of your calculate, no, the previous plot where the leftmost bin, which is kind of where you get this inference from. So this is 10 megaparsecs. Is this like M87, like one object, or is it more than one?
No, this is like, I think it's, we actually have quite a few. It's very interesting because we have quite a few Compton thick AGN within 20 megaparsecs, probably 4 or 5 out of like the 20 or so AGN we have in this bin, somewhere around there. Actually, if you look just at the 3 closest AGN we have, 2 of them are Compton thick. So this is already telling us, this is actually a plot I could have shown, this is already telling us that this is very, very common. It's just we don't see them because they are so damn hard to detect. And indeed, with the fact that as you go towards higher redshift, the fraction of obscured sources increases, this means also that there is a lot of these objects that we are totally missing at high redshift. And you can imagine that when the universe was younger, and I'm talking about redshift 2 and 3, and you have also the peak of star formation, then there is much more gas available in the nuclear region. So in principle, you could expect really a very high fraction of heavily obscured AGN that are accreting relatively rapidly. And this is something that we see also from the cosmic X-ray background. This is the integrated emission of our resolved AGN. So this was discovered in the 60s, actually just a couple of years before the SMB. And you can see that the shape of this cosmic X-ray background actually can remind you of heavily obscured AGN, right? Because if you remember, the unobscured objects, they have a very straight power law-like continuum. And here you have actually a peak at 30 keV, which corresponds to the peak of this reprocessed X radiation that you see once you are depleting all the photons coming from the X-ray corona. So from fits and synthetic population models of this cosmic X-ray background, people have been finding a fraction of this Compton thick AGN that goes up to 50%, and which we are still blind to. So the question is, are we missing a large number of heavily obscured AGN, and how can we move forward? And this is where the millimeter continuum actually will be extremely useful. One potential additional source of complication is associated to mergers and AGN mergers in particular, because we know from simulations that when you have two or more galaxies colliding and then eventually merging, a lot of the angular momentum of the gas in the galaxy is depleted, and this means that a lot of gas starts going towards the nuclear regions. And simulations have shown that actually this is going to increase both the accretion rate as well as the obscuration of the accreting supermassive black hole. So in order to understand this over the past years, we have been studying luminous and ultraluminous infrared galaxies from GHz, which is an infrared survey, with the goal of understanding how often accreting supermassive black holes in mergers are actually heavily obscured. And what we have been finding is that actually out of 60 ULERGs, we were able to detect only 35 AGN. And when we look at the median column density, shown here as a function of separation, actually we are about 2 orders of magnitude above the average that is recovered by hard X-ray surveys. So this means that actually there is much more obscuration in this system. And when we compare the heavily obscured AGN from these mergers with those from isolated galaxies, we actually see something very striking. So this is the cumulative distribution of the column density again. In orange you have AGN that are found in late mergers, and those are systems in which basically the two galaxies are very close, so basically you cannot distinguish the two nuclei. Typically the distance is less than 1 or 2 kiloparsec, and those are the AGN in early mergers, and those here in red with the dotted line are the isolated galaxies from Swift-Bath. And you can see that all the AGN in late mergers actually are heavily obscured, and most of them are Compton thick. So
that's from data?
Yeah, this is from data. And this means that there is an overabundance of heavily obscured AGN in merging galaxies. And now going back to what I was saying earlier, when you move towards higher redshift, you also tend to have more galaxies in mergers, and this means that there is more and more of these objects as we move towards higher redshift.
So Claudio, could
Yeah.
you elaborate a little bit how you know these are AGNs? You resolve point sources in a millimeter?
No, this is actually done with NuSTAR. I should probably have explained it. So those are NuSTAR observations above, basically those are detection above 1020 keV of
but
this.
not from millimeter.
No, I didn't get to the millimeter part yet. Those are all X-ray data. But we are highly incomplete. So there is actually only a tiny fraction of objects that are detected by these hard X-ray satellites. So actually the most extreme obscured AGN in the local universe might be associated to the compact obscure nuclei, which are typically detected by ALMA in HCN. And those are objects in which there is some very strong source of mid-infrared emission just within a few tenths of parsecs, and surrounded by gas and dust with column densities above 10 to the 26. And one of the leading ideas is actually these cones, these compact obscure nuclei, are powered by AGN that are fully embedded by material with column densities above 10 to the 25, even 10 to the 26 centimeters to the -2. And those objects are impossible to detect with any X-ray facility that we have now. And the fact that actually you have such a high covering factor of the material means that there is basically no hope to detect them in the X-rays, just because no flux goes out at these frequencies, and obviously if you do it in the optical UV is even worse. So there is really no way to do it, to just look at the nuclear emission from the optical to the X-rays and hope to find a trace of accretion. So when we look, when we take all these mergers and we look at their X-ray luminosity, so here I'm showing you all these AGN mergers, and they are divided into 3 categories. So here you have the upper limits. So those are all the non-detections of these objects that we investigated with X-ray observations. The stars are the objects that are detected, but they have relatively low column densities. And the circles, the field circles, those are the Compton-Fick AGN, so the most obscured accreting supermassive black holes. And you can see here something very clearly, that all the Compton-Fick AGN, they are actually at very high luminosity. So this could be an evolutionary effect. Could be that they have more material around, so they are accreting more rapidly. But the more likely explanation is that actually we are able to see them just because they are very luminous. So there is actually a lot of objects here that are actually populating the non-detections. So there is a large number of AGN that are non-detected because they are too obscured. And here we are talking about merging galaxies in the local universe. Again, we are working within 100, 200 megaparsec. So the situation is dramatic as we move towards higher redshift. And what's the hope? So this is the question that I've been asking myself for a while. How do we find this heavily obscured AGN? So maybe there is hope. And here I'm saying ALMA to the rescue, because I think ALMA has a huge potential. ALMA or any millimeter facility really has a huge potential to actually allow us to detect and study this heavily obscured AGN. Why is that? So let's go back to our schematic cartoon of accreting supermassive black holes. So you remember the X-ray corona. Those are electrons that are moving in the magnetic field of the supermassive black hole and the accretion disk. So what happens when you have electrons rapidly moving in a magnetic field? Well, you expect to have some synchrotron emission if the velocities are high enough. And there have been studies that have actually started to show that when you look at the radio 2 millimeter SED of AGN, there is a component that appears at tens to hundreds of gigahertz, which cannot be explained by the optically thin synchrotron or the free that one sees at lower frequencies. This is the case for IC4329A. This is a nearby AGN. So here you have, this has a little bit of a jet. It's a tiny jet that produces this radio continuum that you see here. And those are the ALMA data. So this emission, this excess, has been explained by a self-absorbed synchrotron that is produced by the electrons that are also producing the X-rays, or apparent population of these electrons. I say apparent population because it's more likely that actually these electrons are non-thermal, so could be like the non-thermal tail of the electrons in the corona. And from X-ray spectroscopical studies, we know that typically one would expect a few percent of the electrons to be non-thermal.
Do you have an ALMA size measurement?
The ALMA what?
Do you measure the size?
This is all unresolved.
But with VLBI, you could resolve it.
Yeah, with you mean like ALMA with EHT or GMVA? So we have been trying. We have been trying very hard. The problem is that this component is quite faint. It's typically a few millijanskis. So it's quite below. So we had actually a campaign with GMVA to look for this, but he returned just a lot of beautiful non-detections. So yeah, that's. But I'm happy to tell you more about this later. It's certainly an effort that is worth pushing more. So the idea here is that you have these non-thermal electrons that are producing and are coming from very close to the supermassive black hole and are producing this emission that appears at 100 to 200 gigahertz. Okay? So the next thing to do is to look at how this correlates with X-rays, because obviously if they are parent populations, in principle they should be correlated. So the first efforts, they found, well, I mean, a very poor correlation with a lot of scatter. But those were done mostly with beams of 10 arc seconds, 5 arc seconds, and obviously a lot of the millimeter continuum can also come from different non-nuclear processes. So we have started a campaign over the past few years, several campaigns actually, to look at the same sources that I mentioned earlier from the SWIFT-BAT survey. So this nearby powerful AGN, to observe them with ALMA. And we have been carrying out high resolution, so less than 100 milliarcsecond observations of about 25 SWIFT-BAT AGN at distances less than 50 megaparsec. And here the distance cut was mostly motivated by the fact that we wanted to have high resolution. And I'm showing you here just to give you a feeling of our sample. This is the hard X-ray luminosity, and this is the distance. Those are three different classes, so the unobscured, the obscured, and the Compton-Fick. If you remember what I mentioned earlier, we are quite complete in this volume, so basically we can actually have quite a few of this Compton-Fick AGN. And then we looked at the images, and we found that actually they are all detected. So those are 100 GHz of 100 GHz map of this object, and the interesting thing is that they are all resolved or mostly unresolved. And this unresolved millimeter emission appears to be ubiquitous in this radio quiet AGN. And this was the first ALMA survey done with such a high resolution of these objects. And then we went and re-explored this relation between the millimeter continuum and the X-rays, and we found a very tight correlation between the two. So here you have the 100 GHz luminosity, and this is the hard X-ray luminosity. And this is our sample, again, resolution about 1.5 to 23 parsec, and the scatter here is about 0.2 dec. This is actually almost better than the scatter you get between the X-ray and the mid-infrared, which until now was actually thought to be one of the best tracers of X-ray emission. So this is excellent because going back to the whole, my whole discussion that lasted over 20 minutes eventually about obscuration, I was telling you we are hopeless, but then all of a sudden here with in the millimeter we have the potential to reach almost 10 to the 27 centimeters to the minus 2 in column densities. And this is about 3 orders of magnitude above what we can actually do in the hard X-rays. So this can really help us to detect and understand heavily obscured accretion in supermassive black holes.
Why is the limit? Is your millimeter get obscured?
Well, at this point, above this point, you start to be optically thick even at 100 GHz. So, but let's not be greedy. I mean, I'm very happy with this. So then we compared, basically, we looked at this ratio and how it changes with column density. You can see here there is not much of a trend. Same thing with black hole mass. Adding-to ratio is the same. And this is the star formation rate. So this is telling us that we can use actually this millimeter continuum as a proxy of AGN activity over a very wide range of all these parameters. And moreover, we can actually use it to measure column densities. So here I'm showing you for our sample the ratio between the observed X-ray emission and the 100 GHz continuum. So this is the average for the unobscured sources, and this is the column density. So you can see that as you go towards higher column density, you have a decrease in this ratio, which is caused by the fact that your X-ray emission is obscured while the 100 GHz emission is not. So from this, basically one can have some constraints on the column density. We did the same thing, the same exercise of comparing X-ray to millimeter, 200 GHz. So this is work that was done by Taiki Kawamura, who was a postdoc working with me, is now a faculty at Osaka University. And what Taiki did was to use archival ALMA observations of about 100 AGN at redshift lower than 0.05, always selected from the SwiftBAT sample. And here I'm showing you the typical resolution that he was dealing with. So those were archival observations. Obviously, there was a lot of different beam sizes, but there are a lot that are good, so less than a few hundred milliarcseconds. And here he covered a similar correlation, albeit with a little bit more scatter, so about 0.4. But things still look good. And when you divide your population in objects that show and do not show jets, you actually have a slight offset. So the objects without jets here are the orange ones, and the ones with relatively strong jets are the blue ones. And one interesting thing here is that maybe it is associated to the fraction of non-thermal electrons that you have in objects that have strong jets versus objects that don't have strong jets, but this is certainly something that we should keep exploring. When we look at the slope of this millimeter continuum shown here, it is alpha mm, you can see that it's relatively flat, and it's very different from what you expect from just thermal emission, but I will get back to this. I mean, we are very sure that this is something that is nuclear, and it is in no way associated with thermal dust. So 100 GHz is great, correlates very well with the X-rays, same for 200 GHz. What happens if we move at lower frequencies? So this is 22 GHz, this is work done together with some collaborators. 22 GHz versus X-ray luminosity, and you can see that the scatter here is pretty bad again. So why is that? If we go back to our SCD, this is probably because we are sampling different things. So 100, 200 GHz, we are sampling this self-absorbed synchrotron component, and at 22 GHz we are sampling something else. That might be the jet or some free emission. So in principle, we can use this millimeter continuum to actually get some interesting properties about the accretion flow, such as the fraction of non-thermal electrons and the magnetic field intensity. So this is work that we have been doing with the group in Chalmers. This is being led by Santiago del Palacio. And an example is shown here. This is ASIAA 860. This is one of these compact nuclei, which are thought actually to be heavily obscured with column densities above 10 to the 25. And what Santiago has been doing is basically to model all the different components, including a corona, synchrotron emission, dust, and free. Okay. The problem, obviously, is that while the millimeter can be used as a tracer of X-ray emission, if we detect a millimeter continuum, there is no way in principle to say that that for sure comes from an AGN. Could be something else, could be some nuclear star formation, could be plenty of things. So the question we ask next is the millimeter continuum emission in this radio-quiet AGN variable? Why? Because variability would actually allow us to say something, to basically say whether a source is an AGN or is associated to something else. So there have been some efforts. This is a paper from Ehud Behar in 2020, where he found for ISO 150 over several months, couple of months, some variability. You can see here. This is another effort that was done by Pier-Olivier Petrucci. This is just ours. This is a nearby object that was studied with NOEMA. You have, let's see, this is the X-ray in red, you can ignore it. And in black you have the millimeter continuum from the calibrator, and the source is in blue. And so here there is some variability, so great. We decided to do a large campaign with several X-ray telescopes and ALMA for IC 4329A. This is work that is led by another postdoc in my group, Elena Shablovinskaya. And this source was selected because it's very variable in the X-rays. As you can see here, those are all the data from our campaign. And you can concentrate, so this is the X-ray, this is the X-ray minus this trend in the middle panel, and in the bottom panel you have ALMA. And what you can see here from the ALMA data, and I'm gonna zoom in here and compare it with X-rays, is that over the 10 days of our campaign, actually the millimeter continuum was much more variable than the X-rays. So the X-ray go up and down 30-40%. Here you have almost a factor 3 within 1 or 2 days. So this is telling us that the emission is very compact. You can
Let's do the VLBI when it's a factor of 5 brighter.
Yeah, it would be great. But the problem is that how to trigger such a thing. I mean, an object like this, in principle, we could try. we could try to do some VLBI. I need to check because GMVA by itself, I think you need 40-50 millijansky. GMVA plus ALMA does better, but I don't remember exactly what's the limit. But I think you're really borderline here. So next time any of you is in ALMA tech, keep in mind this, that is potentially...
But if you do LMT to ALMA, I think that'd be not an issue.
Yeah, no, I think it's still on the low side, but of fluxes.
For LMT?
LMT?
Yeah, the 50-meter dish.
LMT plus GMVA. LMT plus ALMA.
That alone gets you below that.
I don't even know how to do that. I mean, this is part of the global GMVA.
No, it's part of VHT. You have to talk.
Okay, but you will need to do it at 200 gigahertz.
No, you can do that. You can do
At 100.
Yeah.
But I mean, 200 gigahertz would be fine.
Do 100.
Okay, but that's something that I would certainly love to explore.
So just talk to Daniel.
Okay, you have been doing this. Fantastic, unexpected and fantastic. Great.
I watch just SMBH stuff, not
Okay.
your stuff.
Yeah, but you should. Okay, so this is just to tell you that this millimeter emission is variable and can be very variable. This is another case. This is Argajit Jana, another postdoc working in my group. And here he studied so-called changing look or changing state AGN, which is an object that shows very strong variability on short time scales. And you can see this here. This is light curve, hard X-ray, soft X-rays, and this is ALMA. And you can see that actually the millimeter continuum, in this case 230 gigahertz, follows again the X-rays, and it's very variable. So in principle, millimeter variability could allow us to identify the most obscure AGN in the local universe, because if we are looking at some of these candidate heavily obscured AGN, possibly mergers, then if we see variability on short time scales, we can be sure that there is an accreting supermassive black hole that cannot be detected in any other way. So in principle, this might open a window to detect this huge population, we think it's huge, of heavily obscured accreting supermassive black hole. And one thing I'm very excited about is the Atacama Large Aperture Submillimeter Telescope, ATLAST, which will be hopefully a 50-meter dish, the Atacama Desert, close to the ALMA site, which is going to have a field of view of several arc minutes and a resolution of few to tens of arc seconds, and is going to be doing SDSS-like observations of the extragalactic sky. So this is going to be potentially great to detect both transient events associated to supermassive black holes as well as heavily obscured AGN.
So your goal for this is to look at 200 gigahertz for time variable?
Yeah, this you can do it also 100. So this goes from like 80 or so.
Yeah, 50 meters today.
It's all there.
It's already running, just observe. And
Yeah.
the one that was 100 and 200 gigahertz today.
Okay.
And it's got a big field of view with 5,000 pixels.
You don't need a high
It's the same size. It's the same size.
But you don't need a bigger field of view. You just hit the point source.
I mean, just scan. So just look for time variable sources. You could just use Cortex for
Potentially, yes.
time variables.
Yeah. Yeah. No,
It's
it's.
the same size. It's already built.
Which telescope is this you're talking about?
LMT.
LMT.
50 meters. Same size.
Okay.
The Toltec will 3 bands simultaneously.
Exactly, yeah, exactly.
You get a slope.
Exactly. And you get
Yeah. No, there is plenty of fun things that one can do. Absolutely. And I think, there is. I'm hoping that this will be a main way to actually study these accreting supermassive black holes. So I'm concluding here with my summary. I told you how X-rays can be a very useful probe of the innermost regions of accreting supermassive black holes. Alas, they are useful up to a certain point because most AGN in the universe are obscured. In principle, the millimeter continuum can help us to detect these objects. We have seen that this actually can be a great proxy of AGN power over a wide range of column density, black hole masses, and interracial star formation rates. And this continuum could be associated with the X-ray corona. And this obviously has also an enormous potential to study the properties of the X-ray emitting plasma, something I didn't focus on much during the talk, but already constraining the magnetic field of AGN with SED studies could be extremely interesting. And the huge penetrating power of this millimeter continuum can also be used to infer obscuration and to detect this AGN up to column densities of 10 to the 27. So yeah, I'll stop here and take any question. Thanks.
Thank you, very nice talk, excellent results, really fantastic. And so my question is, actually we know this is a millimeter peak for a long time for the low luminosity AGNs, right? It's like SMBH star and other like M81 star, whatever. So I was curious, actually the peak seems to be similar. Now you apply this to basically to the very quiet AGNs, real AGNs, right? So why the peak? Because the peak is determined by the opacity of the synchronization. Why the opacity is kind of similar? I mean, fundamentally, of course, the accretion process is kind of different. Like when it's hard accretion, supposedly, like for low luminosity AGNs. Now you're looking at the accreting disk. So I'm just curious, do you have any thoughts on why the peak should be similar?
Well, I mean, there are several things, right, that influence the peak. I mean, you mentioned opacity, of course. The magnetic field is the other one. In principle, what else do you have? Like the fraction of non-thermal electrons could influence the location and intensity of this peak.
It's a combination of that. But the peak is fundamentally determined by the opacity.
Yeah, no, I don't have a good answer to this. That's an excellent question to.
Proposing to corona at a constant depth of order 1 at a temperature
of why same for the low luminosity AGNs and the supposedly higher luminosity?
Well, but he's proposing the same temperature.
No, well, in principle, in the low luminosity AGN, you have something else that is producing this this millimeter continuum. Maybe the two things are actually connected, and this goes back to this correlation I was showing between the radio quiet and the radio loud. So now the radio loud are mostly like the objects you're thinking about.
So you say that maybe actually intrinsically physically they are very similar.
They are very similar.
So-called corona. I never understood. It means AGN corona, which people say it's a cloud up there, which moves around. I never understood that.
No, it's still something that we don't understand very well. And also there seems to be a continuum in X-ray properties when you go from your radio quiet, radiatively efficient to the radio loud, radiatively inefficient objects such as those you are mentioning. So in principle, I think there is a continuum of properties. We are just struggling to understand what they have in common. So I think the way you pose the question is actually very useful because it's a very good question to address and goes back to, I would say, maybe the importance of non-thermal electrons as you move from one state to the other.
In a sense, corona and ADA are similar.
You think so?
I mean, corona about the standard disk and ADA as a corona itself.
Because corona is a very phenomenological model.
No, it is very phenomenological.
So actually, from the corona, you can, from low luminosity AGNs, you can simulate it, right? People do the like MHDs, GHz, you can simulate it, producing more or less this kind of spectrum you observe. But the real AGN corona is just really the.
No, simulations don't touch that.
Yeah, don't touch that. It's phenomenological. But now you seem to indicate that from observations they have similar kind of peak at least.
Yeah. Right. The difference with the ADAF is that the ADAF is going to be much more extended, and it's very hard to explain the variability you see in the X-rays with something of that size. But then again, I mean, there must be something, as you say, in common between these two phases.
I thought about this question for a while. So of course you hear the much more massive black holes. The time scale is much longer. And so for the low luminosity AGN, like SMBH star, you have flares. So for more massive systems, then all the flares will
wash out.
They merge together. So that will be the corona.
Yeah.
For experts,
as long as magnetic field strength and electron number density are comparable, then synchrotron properties will be similar.
Maybe we can move to the next question because we have very few time. You can keep this conversation.
So to put another number to this, what's your polarization? What's the polarization like in ALMA?
Great question. So we actually had Elena Shablominskaya. She's preparing 2 papers on the first campaign that we had with polarimetry. So she studied 3 of these objects from our original samples that are nearby at 100 GHz with ALMA. And what she's finding is that out of the 3, only 1 is detected in polarization. So the upper limits of the other 2 are of the order of less than 1% of polarized flux.
Maybe if you go to higher frequency, like Saturday star at 200 is weakly,
Yeah.
100 is depolarized.
And the one that is actually detected, the position of the polarized source is actually offset from the center. And it's actually probably associated, it's NGC 3783, is associated to the strong outflows that we see. And they might not be like, but in principle, so we have been thinking quite a bit about this, mostly Elena, because she's the expert of polarization in the group. But in principle, you can easily depolarize with the opacities that you have in the corona, any intrinsically polarized flux.
So how do you depolarize?
With Faraday rotation, from what I understand.
No, but then just have higher resolution. I mean, the Faraday rotation you can tune to anything you want.
Yeah, but here we are going, well, define a high resolution.
Spectral resolution.
Oh.
I mean, what are you worried about? Depolarization because of lack of spectral resolution, or because magnetic? So if the magnetic field is constant over your emission region, then you get no depolarization. I mean, that's what you
But the magnetic field might be disordered, right? I mean, we really have no clue what is the distribution of the magnetic field on the accretion disk, particularly in the close regions.
In the what region? In the corona.
Yeah. So I don't know. You are saying you would expect very strong polarization from something, even with very high opacity from
I
the.
don't care about that, because if you say let's look at one of your flares to be more specific.
Yeah.
I don't know whether you have polarized data during your flare.
No.
Okay, why don't you have polarization? Just check the box and you get polarization.
Yeah, probably it's something that now we are learning to do. But yeah, in principle, that would be nice.
Because as you're flaring, presumably it's some event, let's say a reconnection event that generates energy. Presumably that's what's happening in a flare. And then you're looking at some small region. That's the fact that the time scale is short. You know that the emission region is very small.
Yeah.
And then the magnetic field just has some causal size, right? So you would think certainly during the flares, it should be fairly highly polarized. You know, there's causality here.
Yeah. No, I mean certainly this was just a first step to try.
Then you get to measure rotation measure.
Yeah.
In which case you actually get to disentangle the B and N.
But it could be even circular polarized, not linear polarized, like SMBH stuff.
Well, that is at low frequencies. It's sort of tiny, it's like 2% circular, and that's the thing that doesn't depolarize. So circular has the advantage is there's no Faraday depolarization.
Yeah.
So in fact, I don't know if you've looked at circular.
I think Elena did, but
No circular.
no, I mean there was no polarization whatsoever.
No circular even.
Yeah, nothing.
But again,
And with pretty stringent upper limits, 1%. So.
Any other quick question?
So I was wondering about the continuum of the millimeter. How high does it actually go in frequency? Because, and also compared to the integrated dust continuum, how strong it is? Because as we step, because millimeter in this range is pretty much the only region where we could actually study star formation in age and post galaxies. So wondering if this is going to affect the future studies that we need to consider this.
You mean like at higher frequency?
Yeah, because like this is 200 gigahertz already.
Yeah.
And if you have like redshift 1, then this what means if you have a band in ALMA that brackets this, then basically what we're seeing is contamination by agent emission also. And this also ties into the agent luminosity. So if you have a higher luminosity like redshift 1, you can easily get a red LX of 44.
Yeah.
Yeah, then the star formation estimation from continuum emission can be affected at this point.
so this is point-like. Whereas
Yeah, but it's point-like, but when we observe high energy galaxies, we cannot distinguish either between host galaxy and AGN. They're all blended together.
if you do a BI, then you will know.
Yeah, it's easier said than done. But I mean, my point here was the key is variability to identify these objects. Then to get a good constraints on things like star formation, yeah, obviously that becomes more complicated.
Yeah. 200 GHz is a sweet spot. For, for rest frame, 200.
Yeah, I would say even lower frequencies, like maybe 100.
Yeah, it's around there.
Yeah, around there.
Okay, so I think time is up, but Claudio will still be here until Friday. He's sitting on office 1108.
Yes.
Yeah, so people are welcome to talk to you.
Yeah, of course.
So let's